Part two. Okay. All right. Yes.
It was on the whiteboard before, but now it was like what you want string theory to do, just to predict things at any arbitrary high energy scale principle.
Yes.
But for instance, it could be that nature has some uncertainty, some physical uncertainty. And actually, on the other whiteboard, you wrote, for instance, that this is under very energetic high energy particles from black holes.
Yes.
So in that case, we would say that maybe I cannot probe those distance scales
Yes.
due to black hole formation.
Yes.
So in that case, you would rephrase that saying that you want string theory to predict black hole formation if you scatter strings, right?
Yeah, but that's what I meant. Indeed, there was a broad statement about all possible physics in all possible regimes. That's what I meant. Yes. Like the idea is that, for example, in asymptotically flat superselection sectors, that the S matrix be well defined for all kinematics, right? Regardless of whether this ends up in black hole formation or not. Any other questions? Okay, so let me actually put the timer, which was exceptionally useful earlier. Okay, all right, part two. So I gave a hopefully clear and extensive motivation for, why strings and what more or less strings do not, and whatever. Now it's time to actually build the theory, and we gotta, we walked so we could run now, because this is the beefiest part of the whole plan, which means that if we don't manage to do the whole thing, either I go, twice the speed, or we bleed into part three and four tomorrow, because they are somewhat, less contentful than this one. So here are most of the technical details of the construction of the theory. Once we build the theory, basically the rest is going downhill. Everything is like, we know how to do things and we compute things and we see what happens. This is the most technical part. So again, please stop me at any moment if I'm not being clear enough. More details are in the notes, and what is not in the notes is in the references cited in the notes. Okay. So I tried motivating. So motivated strings. By strings, of course, I mean relativistic quantum strings. Should be obvious. So how do we actually build the theory? Well, again, we are using the crutch of weak coupling. It will mean something very specific quite soon. And I kind of also motivated that it's not just a crutch. It may be actually necessary because of control issues in four dimensions and other considerations. But even if it was just a crutch, we use it, we start there. Cool, so what do we do? Well, we want to do weakly coupled closed oriented strings, which means like only loops like this. Okay. So, in general, you could have four broad regimes in the theory. So one is the axis of the coupling, right? So in string perturbation theory, the coupling is called G string. And now you will tell me, well, you told me there are no free parameters, but coupling is a parameter. But it's not. I will explain why. It's a dynamical quantity. It's a vev of something. It's related to the expectation value of a dynamical degree of freedom. So this is the thing. Let me put like this is the regime in which it's small, right? And then there is the axis. Let me put it here so they converge here of curvatures, right? So the axis of what I like to call tameness. There are other uses of this word in the field. That's not what I mean. Here by tameness, I mean that the part of space-time that is big, the part that we see, is nice and weakly curved. Curvatures are small because that's, first of all, that's what we see, that's what we care about. And second, that's necessary to talk about an effective field theory. That's what effective field theory means. Scales, energy scales are small. If they're not small in the vacuum, they cannot be small in any observable, right? So curvatures, collectively called with this like curly R, contain Riemann curvatures, so gravitational curvature of the tangent bundle of spacetime, and Young-Mills curvatures of gauge fields, curvatures of scalar fields, which is just, the square of the derivative. So all the curvatures, right? And they should be, so this is the curvature axis, and they should be in the tame regime, they should be um, much smaller than the cutoff square, right? Units of curvature. And again, this is fixed by the precise setting in the theory that we choose. So what we care about is this quadrant, right? This is nice. So what happens here? So the whole column here, this is EFT, right? This is where we can apply EFT at low energies. Of course, you can start in a nice and tame space-time regime, and you can still scatter things super hard, and eventually you get out of the EFT. But at low energies, there is an EFT, right? In the whole thing here. Then here, this is weakly coupled string theory. So let's say this is EFT, and this is well, let me call it string perturbation theory. This is an acronym that you may see around, so I'm just putting here SPT. Not like the acronym in condensed matter, symmetry protected topological phase. Okay, so this is the nice corner we focus on. This is where string perturbation theory is valid. This is where EFT is valid. So what is this? This is a weakly coupled, highly curved space. So it's you can actually deal with it in string theory. You can actually probe highly curved spaces, at least up to some scale way higher than the cutoff. So this is actually pretty cool. It's a very cool sector. Lots of people are studying these things, and they have been studying it for decades. This is a really, really cool sector because you see in this sector, being a low energy or energy per particle energy densities means that strings are sort of rigid. The tension of strings is very high relative to the scales we probe, which means they're tough, right? So if you look at them from afar, they look like particles. Therefore, effective field theory at long distances. But here, there is no EFT. Here, strings are relatively tensionless, or sometimes even exactly tensionless. So they become wobbly and giant relative to the curvature scales. This is a very cool regime that has absolutely no analog in QFT. So it's a very, very cool regime. Not for today, nor tomorrow, but still. So this is a strongly coupled EFT. So sometimes you can actually treat it, usually with the crutch of supersymmetry or maybe more. So it's hard. It's hard, but doable, let's say, in some corners. This is just way too hard. There are some very limited tools we have to access this. Non-zero, I would say. There are some tools we have, but relative to this corner, it's not even close, right? Luckily, this is what we care about for phenomenology, right? So might as well stick to this. Cool. All right. So this is what we want to do. How do we do it? How do we build this theory of weakly coupled strings in time space-time? Well, usually we build theories by spelling out some action principle, right? Except there is no action principle for string theory. Let me be more precise, because I know some people are screaming, but the world sheet. But Polyakov, so what I mean by there is no action is that string theory as a theory of quantum gravity in space-time has no action principle. That's what I mean. Now, there is a formalism which is a part of string theory. It's not separate from string theory. It's part of it. It's called string field theory. It's sort of an approach to do something that looks like an action principle. Works well for open strings. But remember, open strings don't have the gravitational part. Is that a coincidence? Probably not. I think not. But remember, if you have open strings and you make them interact, eventually they produce closed strings, therefore gravity. And the closed string sector cannot have a fundamental action. String field theory produces for us an effective action. An effective action which is effective in a way broader sense than this effective here. So it's not a QFT action, it's something much, much broader that contains all the infinite towers of oscillations of strings. It's much, more powerful in the sense, although it's only perturbative, so it doesn't work in the other corner. But still, the fact that it's a merely effective action, I mean, it's still amazing, still tells us that there is no fundamental action principle for the theory. And it's not surprising because string theory is not a field theory in spacetime. Simple as that. We have no reason to expect to be able to formulate such a thing. We just said that Luca just pointed out, for example, that black holes and black hole formation and things like that, they make the notion of spacetime itself blurry in whatever UV regime, right? So it's not surprising that we cannot just write an action in spacetime. In some regimes of the theory, and if this is the fundamental action, it should cover all the regimes. In some regimes of quantum gravity, space-time is kind of an emergent thing. It's not like a fundamental entity, right? Unlike the asymptotic boundary, which is super selected. So again, it's not surprising that there is no action, right? In general. There will be an effective action because there will be an effective field theory. So fear not. But the starting point cannot be a fundamental action of a space-time theory, right? So what can we do? What can we do? Well, there is a sort of a methodological philosophy in physics that some people embrace, that if you don't know how to do something to progress, you look back at what you know how to do, and you try to do it in a way that does not hinge on the things that you cannot use for the other thing. So for example, here we cannot use a space-time action. Great. So let's look back at what we know how to do. Relativistic quantum field theory in space-time. We know how to do that, right? Kind of. In that case, we do have an action formulation in space-time. We have heard about it extensively so far. But there is another way. There is another way to avoid using actions in QFT, non-gravitational QFT, or even gravitational EFT. We can avoid this. So can recast. Let me call this for short QFT. What I mean is non-gravitational relativistic quantum field theory and or gravitational effective field theory as a quantum theory. This is what I mean by QFT. And interestingly, and fine for us, this is only true for perturbative QFT. So we can recast perturbative QFT without an action principle in space-time. So we can do this. And if we do this, we will learn about how to do the same thing for strings. Because again, it works for perturbative QFT. It will work for perturbative string theory, which is the core that we're looking at, right? It won't work for full string theory. But still, this is the corner we care about. So how do we do this? Well, it's easy. Like, take a time machine, go back to the other day and watch the Gong Show by Filippo, and you will learn all about this formalism. This is the word line formalism. So the key point, at least the way I see this, is that perturbative quantum field theory in space-time is a theory of interacting particles, right? Particles emerge in a weakly coupled regime. So your favorite Feynman diagrams can be seen as like processes that involve word lines. What I'm trying to say is that usually textbooks tell you that this is not an actual process, it's just a piece in a series or whatever. Yes, that's true in the space-time picture, but in the world-line picture, you actually take this seriously as an actual thing that the actual particles do. So you sum over all of these configurations, right? So the world-line approach is based on the idea that we can take like our little world lines. We can take like our world line, let's call it W, world line, embedded in our space-time, let me call it M, for manifold, right? Or space-time. So we have our little world line, and we can formulate an action principle for that, right? It's pretty easy. Turns out, if we do a one-dimensional, so this is a one-dimensional manifold, which means it's a one-dimensional quantum theory. So it's QFT in one dimension, let's say. So this by itself will tell us about free particles propagating in space-time. In order to make the particles interact, right, all the possible ways, right, whatever, what we need is not one-dimensional QFT. Turns out we need one-dimensional quantum gravity. So it's a bit of it's a rhyme. So we're starting from one-dimensional quantum gravity to describe not just a world line, but a sum over all possible world lines, including vertices. And we get to perturbative QFT. So this is on the world line. This is on spacetime. It's an embedding, right? So this is the rhyme, so to speak. It's not a perfect rhyme because this is gravity and this is not, but or rather, it can be. There can be gravitons here, but there will be gravitons in an effective field theory, right? Not a full UV complete theory. So this is the approach, and it just recovers what we know. But it does so in a new way. Well, not new, it's not particularly new, I think, but it's a way that enables us to go to strings afterwards. Because, we have this. Once we have this, we can go from one-dimensional quantum gravity, we can go to two-dimensional quantum gravity. And instead of looking at world lines, we look at world sheets. So instead of the little diagrams over there, we will have like the world sheet swept by a string. Right? Yes.
Before you continue, there's a question in the chat. In non-inertial reference frames and in curved spacetime, the very concept of particles blurry and ill-defined, for example, Unruh effect, Hawking effect, etc. What justifies taking particles as building blocks if they are not fundamental?
Good question. So what I mean by particle is, a unitary reducible representation or a state corresponding to a unitary reducible representation of the isometry group of the asymptotic boundary of spacetime. So it doesn't matter if the bulk is curved and weird. What matters is that there be an asymptotic boundary which is super selected, and I can define observables there in gravity, etc. Yeah, that's what I mean. Like, what matters is that the incoming stuff at infinity be classified by whatever symmetries the infinity has. Then in the middle, a lot of things can happen. Yeah, that's sort of the angle I'm coming from. And actually, in string theory, we don't have a choice. We have to do this, and this will come clear. So, for instance, if I do, a particle in flat space-time, for example, or in weakly curved space-time. So this is actually an alternative, more technical answer to the question is that in a tame space-time, the leading order piece in the curvature expansion is just flat space-time. Right? Simple as that. Which means that at leading order, you can talk about particles and do your calculations, and then curvatures become corrections to this thing. And if you do this thing in flat space-time, you do recover, you can actually talk about particles all the way through. But even if you couldn't, what I ultimately care about is the asymptotics, like being able to talk about particles in the sense of the asymptotic boundary. And again, I was saying in string theory, you're forced to do this because here in the world line, you can do these little diagrams to compute propagators or scattering amplitudes. Like propagators meaning correlators. In string theory, there are no correlators. There are only scattering amplitudes. They lose gauge invariance. And this is the way that string theory has to tell us about what I was telling you before from purely EFT considerations. So I hope this answers the question. So yeah, this is sort of the roadmap. And you see here we have.
The spectrum string from the Lagrange.
Is that a comment or a question or?
Write the Lagrange.
You mean a two-dimensional?
Spectrum string.
You mean the two-dimensional Lagrange, like a worksheet? Yes, of course, of course. But this gives you the single particle spectrum. That's very important.
You get all the spectrum string.
The single string spectrum.
The interaction.
Exactly, exactly. Yeah, but that's exactly what I'm going to do. Yeah. But this is what happens in the world line as well. Like the world line gives you the single particle spectrum. The interactions produce multi-particle states, or well, I mean, even if you don't start with them, generally particle number is not conserved, and so on. Yeah. So let me be super clear here. This is a quantum mechanical system in one dimension whose Hilbert space contains single particle states. The space-time theory, Hilbert space, has all the multi-particle things, right? So if you forget about the Higgs theorem and so on, the free Hilbert space is the Fock space over the single particle Hilbert space. Let me just so the space-time picture and the world line or world sheet pictures are related in this way. Like this is what we're gonna do. So here we will have two-dimensional quantum gravity, right? And will correspond to perturbative quantum gravity in space-time. So let me call the worksheet sigma for surface. And this will be quantum gravity on whatever, perturbative quantum gravity on this M. All right, so this is it's a closer to a perfect rhyme in this poetry metaphor that Witten put forth a few years ago, more like 10 years ago. Okay, so how does this work? Well, you see, the world line QFT is a one-dimensional QFT, or barely a QFT, can have multiple actions, right? I can write an action, but I can write more than one action. So in this correspondence, a 1D theory, like different theories, give me potentially different QFTs, like theories will give me QFTs. They could give me different theories, or they could give me different vacua in the same theory. Whereas here, in principle, you would say the same, right? Different theories, they would give you different QGs, right? But actually, that's not the case. They can only give us different vacua of the same theory, right? So at the perturbative level, this is not quite completely true. You will get vacua of the same theory or different perturbative sectors, different perturbative limits of string theory. But non-perturbatively, we have very strong evidence that they are all connected by string dualities. It's a very esoteric thing I'm not going to talk about. But the upshot is that different worldsheet theories will give us vacua of the same theory, one theory. So this is a crucial difference. And there is a good reason for it, because one-dimensional QFTs and one-dimensional quantum gravity and two-dimensional quantum gravity are very different. So this is a very important point to keep in mind. Right? So recap, we have this perspective of working on the world line or the worldsheet instead of space-time. Space-time appears in the theory, of course, but indirectly. Okay? So sometimes you will read stuff like different string theories. What this means is different worldsheet theories that describe perturbative limits. But the theory is only one theory with different limits. Yes. Yes. Which is exactly what I was going to do now. So what does 1D quantum gravity mean? Well, exactly what it means in 4D or 76D. What it means is that you have some, let's say, some action for our world line. Okay. So what fields will our action depend on? Well, naively, there's at least one field that it absolutely must depend on. because there is the space-time picture. The world line is embedded in space-time, right? So at least something must be there, which is the the coordinates of the world line as a function of whatever coordinate you want on the world line, proper time, for example. So these fields must be there. Why am I calling them fields? Aren't these just coordinates of a particle? Yes, in space-time, but on the world line, you see they are fields on the world line because they depend on the coordinate on the world line. And this mu index has a local meaning in space-time, as in they are local coordinates on a manifold. But on the world line, it's just some index of a global symmetry, of an internal symmetry, right? From the point of view of the world line, these guys are scalar fields. They're just a bunch of scalar fields. How many? Many. Dimension of space-time, many scalars. So this must be absolutely there. There can be other fields, and in general, there will be other fields. And then, to answer your question, there will be a dynamical metric on the world line. Let me call it gamma instead of G. G is the space-time metric, gamma is the world line or sheet metric. So there will be this action, right? And there is a term that must be there. So remember, what is so either you already know the answer of what the action is, or you can use one-dimensional effective field theory to figure it out. Like you can just write, let's say, what kind of terms must be there? Well, there will be some integral d tau, right? And then diff invariance tells you there's minus gamma, right? And then what kind of terms must be there? Well, EFT, start with two derivatives. So there will be like x dot nu, x dot nu, and then the space-time metric evaluated at x of tau. Right? This term is the leading term in an effective field theory on the world line, the two derivative guy. Then there can be a cosmological constant. So there can be like a term. I call it m squared because it turns out the 1D cosmological constant is the mass of the particle, funnily enough. And then there can be other terms, right? S stuff. There can be other terms, other fields and whatnot. So this gamma, which is, sorry, there is a gamma tau tau here, right, by covariance. This gamma is a one by one metric tensor on the world line. So what I mean by quantum gravity on the world line is that in this theory, gamma is dynamical. This is what it means. It means that, well, where do I write this? Let me do something like this. So it means that, well, actually I can just erase this. Where are the, oh, there's also another one. Okay, thanks. As always, I didn't optimize the amount of effort. Like I really want to be lazy, but I really want to do the least amount of effort, and yet life gets in the way. So, so what one-dimensional quantum gravity means is that whatever observable I compute in the theory, observable, for example, again, in non-gravitational QFT, I can compute a propagator, or even in perturbative quantum gravity, I can, like as a field theory, I can compute a propagator, like Luca showed us. This is one example, or a scattering amplitude. This thing will be given by a functional integral over our x fields, for example, for sure. Then there could be other fields. We will comment on this soon enough. And then the dynamical metric. And then there is a diff redundancy because it's dynamical gravity, right? And finally, this is super important, at least at this level, it's very easy to do, the sum over topologies. So we sum over the possible world lines at fixed conditions, whatever endpoints we have at infinity, at some fixed points in space-time, whatever. So we sum over world lines, which means like, if we have 4 points, we could have like this, or we have like this, or whatever. So the sum over world lines It's a sum over one-dimensional, possibly singular manifolds because they have vertices. I will comment on this soon enough, but this is what it means. Then, of course, you have your garden variety Euclidean action of our fields, and then whatever thing computes the thing you want to compute. I'll elaborate on this. This is the schematic structure. This is what I mean by 1D quantum gravity. I hope that is clear. It's exactly the same for the worksheet, by the way, with a couple of very important differences, which will ultimately be crucial. Yes. So they are almost everywhere. You can consider them one-dimensional manifolds. Exactly. Precise. Well, it's not that they cause problems at this level. So if you have vertices, these are not manifolds. These are kind of almost a manifold. They are manifolds with some singularities, right? Sorry? Well, these ones I wouldn't call orbifolds because they don't locally look like quotients by a discrete group. But actual orbifold, yes. No, I was yeah. So the worst here, the string is, you can think of it as this thing that propagates in time. Does that make sense? Okay. Yeah. It's the contravariant component, the only one, of the 1D metric tensor, yes. Yes, tau. You can call it 0 or tau or yeah. Yes. So here it's Lorentzian because the theory starts Lorentzian. In the path integral approach, we Euclideanize it as completely standard in relativistic field theory. Yes. Yes. This is explained in Polchinski's book, by the way. There was another, yeah. Precisely. Very good. So the thing is, you fix some conditions here. So they could be incoming momenta kind of conditions, or they could be fixed positions like x1, x2, whatever. Right? If you do that, for example, let me look at the simplest case, the actual propagator, right? Like x, y. Right? So the boundary conditions in the functional integral that tell you to sum over all such paths are that the field big X, let's say 0, coordinate 0, is little x, and that x at the full proper time of the world line, let me call it capital T, be y. Right? Now, what is capital T? Well, given a metric on the world line, capital T is just the integral from 0 to whatever extremum you fix. You can fix 1. It doesn't matter. It's coordinate reparameterization invariant anyway of this. And this is a gauging, the only piece of gauge invariant information on the metric on the world line. So it's only the remains. And it comes here, like in the sum over world lines, you will get like an integral over tau, over t. So this is the sum over world lines, sum over all paths that you were mentioning. And actually, this is what I was gonna evaluate now. So is everything clear so far? Okay, so how do we evaluate this thing? Let's say focus on this. This is the propagator at the end of the day, right? Well, so we gotta do the gauge fixing. So you may, I mean, we talked about ghosts a bunch, like Faddeev Popov ghosts, and they show up here obviously because we gotta do some gauge fixing. So we gotta gauge fix diff W, let's say, diff W, right? So turns out, as I was mentioning before from the EFT perspective, in 1D and 2D, you can gauge fix the fields. You can actually do the gauge fixing. In 4D and upwards, you cannot. There is no gauge fixing you can do. You can do it perturbatively at best. Here you can actually do it because metrics, gravity in 1 dimension, 2 dimensions is exceedingly simple. So you can actually do this using the FATDEF Popov ghosts. And so basically you will end up with, won't make the same mistake twice. You can't fool me, whiteboard. So this will be sum over W of like a gauge fixed integral over the fields on the world line, where now the world line action has all the fields, and then gamma is fixed to some gauge fixed metric. For instance, a constant, because it's just a one-dimensional thing with the other insertions, and the ghosts. Now, there is another approach, which is the one that Luca took, where you have ghosts, like CC bar, and a gauge fixing term. Sorry, this is the ghost term. You have a gauge fixing term. There's another way where you have twice the amount of ghosts, like B and C ghosts instead of just C, but you don't have the gauge fixing term. This is the approach that we're taking. So this is just the ghost action, again, with a fiducial gauge fixed metric. And this is what it looks like. And so again, how do we gauge fix? I have the full derivation in my notes because I wasn't satisfied with the ones in the literature. But after I wrote it down, I found a good one in a Bastianelli's notes. So I was like, shit. But that's life. Actually, I found another one in a solution manual by Polchinski, or Polchinski's book. Anyway, I just redid it myself in the notes. So how do we do this? Well, long story short, as I said, the only gauge invariant information about the world line, a single world line, is the proper time, the actual length, nothing else. So there will be just an integral in dt. Now the question is, what's the measure? Is there some other factors? Are there some other factors? The answer is no. It's just dt. And I derived this in the notes. Now, if the world line were a circle, there would be a factor of 1 over t, actually, because it comes from something I'm going to explain. But for the propagator, you get this. This is your fiducial metric. And if you evaluate this, what you get is, you can evaluate this because this is just like, at least the part that concerns the x fields, this one, is just free theory, right? With a gauge fixed metric. Of course, it's free in flat space-time. It's almost free in almost flat space-time, which is the one we care about. So at least to leading order in the curvatures, this will be asymptotically, the first order will be something that you can recast in a very suggestive form. You can use like XMP variables like Filippo was doing in his Gong show. You can recast it in a way that looks suspiciously like a propagator, except this Gaussian integral gives you something like e to the minus t p squared plus m squared, something like that. And now if you integrate over t, you see the integral dt from 0 to infinity, all possible proper times, of e to the minus t blah. This is just the Stringer parameterization of the momentum space propagator from scalar field, a scalar particle. And this is the Fourier transform in position space. So you get precisely what you wanted, which is pretty cool, pretty neat. If you do it for a circular world line, the only two possible 1D manifolds or manifolds with boundary, you get dt over t. dt over t gives you log p squared plus m squared, which, up to usual regularization stories, is just the one loop effective action. So this is pretty cool stuff. And then you can do more, of course. You can compute full diagrams, but at a price. So this is the, you know, basically free theory, essentially. Free Q of t. For interactions, for vertices, there is the problem that you were mentioning, namely these manifolds are singular now. We got a sum over singular manifolds, which means that we gotta multiply these guys, you know, different, we gotta sum over all possible world lines. We'll multiply propagators, but at the vertex, at each vertex, we must put in some rule by hand, put in rule by hand, which spells out what the couplings at the vertices are. You know, you can have any sort of couplings there. And this way you recover perturbative QFT, where the same data is encoded in just a Lagrangian. So in the Lagrangian, where you have like, you put all the possible couplings, the same way you put couplings by hand, you put these rules by hand. There is no free lunch, right? Now, this is cool and all, but you can do even more, as I said. This world line action need not contain just X fields, right? It can contain more. This is just a one-dimensional theory. It can contain other fields. So the general structure is this, right? There is this space-time sector plus possibly other terms like you know, could be an EFT with higher derivatives plus other stuff. Now this other stuff can contain weakly coupled fields like this one, and or strongly coupled dynamics that is actually non-Lagrangian and it's completely confusing. And let's say momentarily we won't care about this, but at least you can include some other weakly coupled fields that you can actually describe with a good Lagrangian. So what other kinds of fields can you have? So for other fields, and I emphasize fields in the sense of a weakly coupled Lagrangian description, right? Which means that they belong here. They belong to the space-time part of the theory. So you see this one-dimensional theory as a part that involves space-time dynamics, space-time propagation of this particle. It can also have other terms like an electric charge coupled to an external electromagnetic field, you know, coupled to the particle. It's like a mu x dot mu, right? It can have these kinds of terms, all kinds of terms. This is the space-time piece of the theory, and this is the internal piece, I call it. So the space-time piece must be weakly coupled. Why? Because weak coupling in this theory means these are the couplings. These are the couplings, right? So these are the couplings of 1D theory. And you see, when is the theory free? When spacetime is flat and there are no other fields. The theory is free. Therefore, if they're almost flat, the theory is almost free. So the couplings, you can infer that they must be given by curvatures. Curvatures. And there is a proper way of doing this. It's called either the geodesic expansion or normal coordinates, sometimes they're called. We will use them in part 3 tomorrow. So the point is that the requirement that the space-time part of the theory be tame, the one that I said before, to match with what we see, tells us that the space-time sector of the theory be weakly coupled. This can be whatever. The internal sector can be whatever. But the space-time part, the one that cares about the Lorentz symmetry or local Lorentz redundancy, is weakly coupled. Therefore, there are only a handful of options that we can have. We can have scalar fields. We can have fermion fields. What else can we have on a 1D theory? Vectors have no degrees of freedom. Gravitons we already have. Gravitinos, okay. Well, basically, we can only add the spinors, right? So fermions or Rarita-Schwinger fields. That's the only option. Pretty cool. So for other fields in the space-time part of the world line theory, we can only have fermions, or let me call this gravitini. So gravitini. Gravitini are just massless Rarita-Schwinger fields, helicity 3/2. And that's what a gravitino is. Gravitino because it must couple supersymmetrically to the graviton if it exists. So that's why it's called gravitino. But the point is that, you see, if we add fermion fields, they must respect the Lorentz symmetry, which at the level of the world line is a global symmetry. It's an internal global symmetry. But still, they must preserve it because they describe the space-time dynamics. Therefore, these guys must also have a little mu index here. This is an index in space-time, not on the world line. The index on the world line is tau. Only one. So these are the only options. Pretty cool. Turns out they are very useful. First of all, if you include these, you must include this. And if you include these, you must include these. So either both or nothing. The reason is if you include these, the theory becomes one-dimensional supergravity. And because you have scalar fields, the x fields, they must supersymmetrize to x plus psi, like fermions and bosons. So there's no option. The other way, if you have fermions, the theory is not supersymmetric on the world line, but it's unstable unless you add supersymmetry. And because you have a graviton, by SUSY you have the gravitino. So my point is, if you have fermions on the world line, must have one-dimensional supergravity. And again, this has nothing to do with space-time supersymmetry, right? This is true in the standard model. Okay, let me be clear. This is true in the standard model, or any other QFT in perturbative QFT in this formalism. This is called the spinning particle formalism. Why? Because these degrees of freedom encode particles in space-time with spin. And this makes perfect sense, because what are the degrees of freedom of particles in flat space-time? The momenta, which are encoded by the Fourier dual of X, and spin, which are encoded by these fermions in a way that we will see for strings. And I will never be able to do it. So this is crucial. So basically, to encode particles with spin, we need one-dimensional supersymmetry. Local SUSY, I mean supergravity, because there's a graviton. Right? So there is no choice in the matter. Okay, so either we do spinless particles or spinning particles, and in this case we have one-dimensional supergravity. We have, either of the two, and we get to choose how much SUSY we have, right? And depending on how much SUSY you have on the world line, you get like different spins of particles in spacetime, right? That's a world line formalism in a nutshell. Yes.
Does not always imply space-time.
Precisely. Yes. Same for 2D, by the way. So this is the world line story. Now let's apply it to 2D. Yes.
Model fits does not have to be weakly coupled, but if I want to do calculation, yes, then yes.
Not just to do calc. So no, if you know.
There's a reason why they should be coupled for model.
Yes, my reasoning, it could be stupid, but my reasoning is that part of the world line fields should be weakly coupled, not necessarily everything, but at least part of it, because it's at least the part that describes the space-time propagation of the particle. And the reason is that the couplings of the space-time sector, the one that couples to the metric and all fields in space-time, the couplings of these theories are the curvatures. And we said somewhere that I raised, we want low curvatures because that's what we see. That's all. It's a thing to eventually match to an effective field theory description. So you see, it's cool, like weakly coupled world line, low energy space-time. It's a correspondence. Now, this other stuff can be strongly coupled, but this describes internal degrees of freedom of the particle, like, I don't know, other quantum numbers. For the string, same thing. Okay, cool. Of course, it could also be the same, but like the same kind of theory, but with extra dimensions. It could be also in here, but it could be anything. So let me just introduce terminology, which is very important. The space-time part, in space-time, it describes like particles propagating, interacting weakly. That's what we said. From the point of view of the one-dimensional theory on the world line, this type of action has a name. It's a very weird name for historical reasons, but the name is, it's a non-linear sigma model. Okay, it was because hadron physics is weird. But non-linear because the theory is non-linear, model because it's a model, sigma because I think has to do with the like mesons and stuff like that. All right, so what was I gonna say? Yes, so this is a name, and it will be the same name here, and the manifold described by this metric, the space-time metric, is called target space in this language. So this is a target space M, right? So if you look from space-time, which is what we do, it's just space-time. If you look from the world line, you call it target space because it's the target of this embedding terminology. But because, you know, originally, like you could have like a weird, well, not weird, but actually less weird, nonlinear sigma model where you start from space-time and you go to some abstract manifold, like a group manifold that describes like a Callan-Coleman Vezzumino construction for spontaneously broken symmetries, for example. Like it's all kinds of applications for nonlinear sigma models that have nothing to do with gravity. But for us, this is the world volume, line, sheet, whatever, of our fundamental objects interacting weakly in space-time as the target space. This is our picture. Okay. So now let's do this in one dimension higher, 2D. So let me put it here. Okay. Any questions? All right. So in 2D, same story. Our world sheet action can be, well, if you take the same thing and you rewrite it in 2 dimensions, the conventions that are usually used are such that this action reads like this. There's the tension of the string. There's a scale that must be there. And then we have an integral over 2-dimensional worldsheet. Now, the coordinates on the worldsheet, I call them sigma. And the integral is over big sigma, the worldsheet. Then there is our metric on the worldsheet. Then we have the nonlinear sigma model part, right? Now we have d alpha x mu. So worldsheet index, space-time index, right? D beta x nu, g mu nu of x. And in 2D, we have some other thing that we can write. So let me first explain something that I think is interesting. Here, we had choice. Here, we can add higher derivative terms. We can do all kinds of things. Here, we have way less choice for 2 reasons. One is that we want this theory to be UV complete. This was merely an effective field theory at best. We want this guy to be UV complete. So we better ask that this theory be perturbatively UV complete. Remember, we want this theory to be perturbative because we want space-time to be tame for phenomenology, for example, for EFT. So this theory should be weakly coupled and UV complete. From Lucas' lectures, you may recall that this requires perturbative renormalizability. So we should write the most general perturbatively renormalizable action that we can. So we don't have like infinite higher derivatives like we could in principle right there. We would if we wanted to describe effective strings, for example, the QCD flux tubes. But in fundamental string theory, we only have this choice. So what is the stuff that we can write? Well, we could write something else in 2D. It's a 2x2 dynamical metric symmetric, so it couples to some symmetric combination. We can have an antisymmetric combination because in 2D, the invariant Levi-Civita tensor is 2D, 2 by 2. So we have this. So we have this combination. Now, this must couple to an antisymmetric tensor in space-time. We call it the B field. Right? This is another guy. And finally, there's another term. And for dimensional reasons, I will do the following. So this is the string tension. And for historical reasons, it's defined as, well, either as m string squared, the string scale, right? Or as 1 over 2 pi alpha prime. This is the scale that you will see everywhere. It has dimensions of length squared in natural units. This is called the Regge slope for historical reasons. It's complicated. But the point is that people will say alpha prime corrections, alpha prime effects, this and that. This is what it means. Effects in the string tension or string scale. And by dimensional reasons, I put it here. And then there's another term that I can write in this bosonic spacetime sector, which is the Ricci scalar of the worldsheet. So it's a two-dimensional worldsheet scalar, Ricci scalar, coupled to some scalar field. Let me call it in spacetime. So this big X means that it's a scalar field in spacetime or tensor field in spacetime, evaluated at the point where the string worldsheet is in spacetime. It's called a pullback, if you're familiar with some differential geometry. So this is the most general thing I can write for just the X fields. But we said there are fermion fields also in the most general action I can write. So I can choose to include fermions on the worldsheet. And this will involve some terms, which involve these psi mu terms, and the gravitino, actually. Gravitino. This is the space-time part. Then there could be something else. There's no reason to exclude it. Other stuff. This part can be strongly coupled. Could be like a weird, complicated theory. We don't care for now, but it's super important for later. So this part, by the way, is called the Polyakov action, or at least the generalization of the Polyakov action. And this is again, the presence of these guys implies the presence of these guys and vice versa, and they imply worldsheet sub C. How much? Well, depends how many fermions there are and how many gravitini there are. So this is required to describe fermions in space-time, well, in M space-time. And you may say, okay, it's just a choice that you can make. You can make bosonic strings or superstrings, which have also fermions in space-time. You can choose that. They can have fermions, they don't have to. But you can choose to do this, sure. But it's been known for a long time that bosonic strings, the perturbative vacuum of bosonic string theory is tachyonic. So you could say, I don't want tachyons, therefore this. But it's been proven, a stronger statement has been proven, so that if you don't have tachyons, regardless of whether the theory is bosonic or superstring, if you don't have tachyons, you must have fermions in space-time in perturbative string theory. And the only way to have spinning degrees of freedom in space-time is to have fermions on the worldsheet that couple to the Lorentz symmetry in the same way as the X fields. So this is completely forced on us by the absence of tachyons. Right? Cool. So we must. Correct. Yes. So this is worldsheet SUSY. The same kind that the standard model has when formulated in, I say standard model, but what I mean is any QFT, perturbative QFT in spacetime. Okay? When formulated with the world line. So this is the general structure. Now, what kind of choices do we have? Like you see, I try to follow this approach where like we exhaust all possible roads, or at least all reasonable roads, and we end up with very few possibilities. So yeah. Very good question. This is what I was about to say, more or less. So turns out, so these fields, right, and possibly other things here, they leave fields on M. And we said the dimension of M is D. Okay. And M is a Lorentzian manifold. It's a Lorentzian spacetime. Now, in principle, you can put however many supersymmetries you want in the fermions. So this is what's called global supersymmetry on the worldsheet. But I said that the presence of these global supersymmetries actually induces some ghosts because these couple to the X fields in the same way due to Lorentz symmetry, and they induce, like, apparently they would induce ghosts. Ghosts from the bosons are killed by the graviton because of gauge redundancy. Similarly, the ghosts in the fermions, classical ghosts, not Faddeev-Popov ghosts, they are killed by the gravitino. So now you could say, oh, then you must have at least one gravitino, right? So the global SUSY, global whatever, okay. But the local part, so the part that is gauged by the gravitino, okay, together with the graviton, the supergravity part, what can it be? It can be two things. Either none of it, and you get the bosonic string, which is tachyonic in spacetime, so scratch that. Plus, it only has bosons anyway, so who cares? And then you have only one option, which is minimal SUSY. I will be more precise later because there's the left moving sector and the right moving sector, but minimal SUSY you must gauge. Why? And this is a beautiful result that is found in Polchinski's book or in my notes. If you gauge more than this, so if your supergravity part is higher than this in terms of extended SUSY, the dimension of space-time must be either non-positive, right? Or it can be positive, but it must be complex signature rather than Lorentzian signature. So the only option for M Lorentzian with D positive is this. How cool is that, right? So we basically have only one option if we want a classically stable, non-tachyonic tame spacetime. That's the only option. So maybe we can unpack this a little bit more. I don't know if I wanted to say something. Yeah, I'll do it later. So another thing we can say is that, again, repeat the same constraints from the very beginning. Spacetime is weakly curved. All these fields have weak curvatures, which means that the theory is almost free, weakly coupled. This means that we can look at the free part and see what it tells us. So what this tells us is that we have a closed string. So let's say, I'm elaborating on this. Right? So this thing describes closed strings. Yeah, you're right. This one, maybe? This one? Okay, thanks. So these are like little loops that propagate in space-time. So they're basically, it's a cylinder at this level, but it will be some other stuff and soon enough. So why am I telling you this? Because you see, this is like the string is a loop, which means that fields on the string describe its oscillations, the center of mass position, and the oscillations around the center of mass. And these oscillations are basically waves on a circle, right? So the Fourier modes of the bosonic and fermionic fields, the weakly coupled guys, right? And again, in 2 dimensions, we cannot have anything else because vectors, like gauge fields in 2 dimensions, have no degrees of freedom. Gravitini are there, gravitons are there, scalars, fermions, everything is there. Everything that we can possibly have in a weakly coupled theory is there. No choice. You can ask, what about massive vectors? They are prohibited by the gauge invariance of the theory. I will come to that. So there's only option, this is the only option. So the Fourier modes of these fields are waves on a circle. waves on a circle. And you may recall that waves on a circle can go both ways, left moving and right moving, right? So we can have left moving and right moving waves. For example, like x of sigma minus, so the time coordinate minus the, the spatial coordinate on the cylinder, or plus. These are the left moving and right moving waves. This means that at the free level, leading order, they factorize, they decouple. I'm going to use this language. They decouple. Of course, the interactions may couple them, and this sector may not decouple in this way. This may, it's a mess. But what we care about is that the leading order piece of the space-time sector has this property. We can talk about left and right, and this is super useful. For example, to connect to this story, if left and right decouple, we have now 3 options for minimal supersymmetry, which we gauge. Right? The 3 options are, so for the world sheet SUSY to gauge, the one that is gauged, we have now 3 options. So what is the minimal amount? Well, either you have nothing at all. So for left and right, you have 0 and 0 supersymmetries that you gauge. This is the bosonic string. Which again, not only it just is tachyonic, it must be tachyonic because there are no fermions. You can also have tachyonic strings with worldsheet fermions, by the way. So yeah, this is one option. Then you have this option, or vice versa, changes nothing, or both, and that's it. You cannot have 2-0 or 2-2 or whatever. You can't. You cannot if you want a good bona fide Lorentzian spacetime. You can't.
You get an ordinary sigma.
Yes, but in a non-Lorentzian target space. In this, no, that's a world sheet. Yes, I agree, but we want d bigger than 4. Yeah, this was the first thing I said. Yes, absolutely. So there are, if you want d at least 4, the only Lorentzian options are these. Yeah. In 2-dimensional space-time, yes. Not particularly surprising because, gravity in 2D is kind of weird. Okay. So these are the 3 options. Now, this is called, well, I should call it the RNS superstring, because RNS is this kind of formalism I'm using to talk about superstrings. And so this means that it's superstring in both sectors, right? The left and right. I'm just gonna call it RNS. I have no time for this. This is, you see, it's RNS bosonic. So it's a different kind of gauging in left and right. It is consistently doable. And because they're different, this is called a heterotic string. They're different, heterotic. Still superstrings because they do have worldsheet fermions. So superstring means worldsheet supersymmetry. It doesn't mean space-time supersymmetry. Cool? Cool. So this is the kind of weakly coupled space-time, tame space-time kind of sectors we can have for the worldsheet. And now, yes. It's an antisymmetric tensor field of rank 2 in space-time. So it's just like any other field that you can have. No. So the field strength is usually called H. H equals dB in differential form notation, or H mu nu rho equals, d mu b nu rho antisymmetrized. So there's this thing, and it's analogous to the electromagnetic field for particles because it couples minimally to the worldsheet. Like you see, this is in differential form notation, this is integral over sigma of the pullback of B under the embedding. And this is exactly the same as the integral over the world line of the pullback of the electromagnetic local one form of electromagnetism. This is a minimal electric coupling, exactly like in electrodynamics. It's just one rank higher because the string is extended. Okay. Well, in the simplest vacua, they are. In principle, they could be massive in some complicated, more complicated vacuum. Yeah, yeah. Yeah, yes, yes, of course. Long range forces. Yeah, indeed. But they need not be massless, and the B field need not be there at all, in fact, because in certain open string theories, it's just not there. Yes.
How do you define this? Like string bucket?
I'm getting there. This is the next thing I'm gonna do. Yes.
Higher than 4, then we can kind of define different atlases because they're maximal, and by different atlases we have different kind of different notation. Yeah.
Right. So
but by the terms in the integral, we have fix the atlases first.
right. So you may, but turns out the result is independent of that choice. This action is completely intrinsic. It's a geometric action. It does not depend on any coordinate choices or any atlases that you choose. I mean, of course, the a atlas is necessary to define what a manifold even is, but the coordinate charts that you pick doesn't matter. Does that make sense? Like this
For different atlases, we don't get different results.
so if the different choice leads to a different manifold, you could.
First we define manifold, then we define some atlases.
The atlas is part of the data that defines a manifold, right? A manifold is a topological space with an atlas, yada yada, right? My point is that this is an intrinsic action. But I don't see your point. So what I'm saying is that if the manifold is given, this action is dependent on the manifold and on the fields on the manifold. It's an intrinsic statement. Doesn't depend on coordinate charts or anything. Okay. So I'm getting to define what a string vacuum is by analyzing the path integral for this thing. Okay. So for now, this is unspecified and this is very Let's do this. Gotta go a bit faster now. So again, we can leverage the stuff we did for the world line, right? So let's just write whatever quantity we're computing. I'm not very specific at the moment. I will be more specific tomorrow. It will be something like this, right? We have these space-time world sheet space-time sector fields. Then we have our metric and gravitino. And then we have the gauge redundancy. Now, the gauge redundancy is what? Well, I will not write this explicitly, right? Let me just not write it. Implicitly, its presence means that all gauge redundancy is supersymmetrized. So instead of diffeos, you have super diffeos. Instead of manifolds, you have super manifolds. It's heavy notation for us, doesn't matter. Let me just not write it. So the redundancy that you have is diffs, sigma, okay? Of course, you gotta eventually sum over the worksheets because it's 2D quantum gravity. But it's not the whole story. This is the crucial part. So turns out, because of how the theory is, the fact that it describes the propagation of a string in space-time, because of this, there must be some other redundancy in this action. This is called Weil invariance. This is one of the crucial differences with respect to the world line. What is Weil invariance? It's Weil transformations are transformations that only act on the metric of the worldsheet, which is an independent dynamical field at this level. And they act by rescaling them by a positive function, smooth function. Right? I'm writing it this way because this is manifestly positive and because I can expand in omega as an infinitesimal transformation. Cool? And the 2 is because it's squared, because it's a metric line element. So this is Weil invariance, does not act on the fields, the other fields. This is Weil invariance. And we always have it. You can check. And it's a gauge redundancy. We gotta take care of it. And then we have our worldsheet Euclidean action and any operator insertions and whatnot. So now we gotta gauge fix this. So in principle, we can do it, right? In principle, what we can do is use a metric has 3 independent components. It's a 2x2 symmetric thing. Differs 2 components to 2 vector fields. I can kill 2. While I can kill 1. I'm only left with 0. I can in principle, I should be able to gauge fix to the flat worldsheet, right? So gauge fix to gamma alpha beta equal delta or eta. I mean, this is the Euclidean, so I'm going to write delta alpha beta. Well, kind of. There are a couple of things. So first of all, even if we could, it would be true at best locally, right? There could be like global topology of the worldsheet. Second, there could be anomalies, right? And third, there could be some deformations of the metric that we cannot gauge fix. These are called moduli. So this means that the best we can do is to gauge fix gamma to gamma hat, fiducial metric, with some parameters t. Let me call them t, right? Or moduli. These are deformations that you cannot gauge fix. Example, a circle has a radius. You cannot gauge fix away a radius. It's a physical thing. But in this case, because of Weil invariance, you could, but now we're dealing with surfaces. For example, like a torus, which is a surface, has like the way that you glue the torus together, which is gauge invariant information. It's a conformal structure of the torus. You cannot gauge fix this away. Okay. Yeah.
Online. Right transformations usually can change a lot the geometry of the manifold. Why are they gauge redundant? Doesn't the shape of the sheet in target space matter?
You would think it does, but it doesn't. It doesn't because the way that the Polyakov action arises is it must describe the propagation of a string, which means that it must be classically equivalent to like the area swept by the worldsheet, similarly to the world line, the proper time. So if you start from there, it's called the Nambu-Goto action, and you go to this framework where you can do the path integral and so on, you unavoidably get Weil invariance. That's the story. And this is actually related to the fact that there are no propagators in perturbative string theory, only scattering amplitudes. Because for Weil invariance, the shape of this thing doesn't matter. You can take these legs and send them to infinity. And this will define a scattering amplitude, right? That's the only physical thing you can do. Right, I gotta move a bit faster, but unfortunately, so you can have moduli and you can have anomalies, right? So again, we are forced on this. It's not like I'm choosing anything. So what anomalies can we have? Well, we can have diff anomalies and Weil anomalies. So I'm gonna be super quick, but you can find more details in the notes. Diff anomalies can be small or large. Now, what does small and large mean? It means that the gauge transformation you do is homotopic to identity. You can make it as small as you want, or you can't make it as small as you want. It's like large, right? You may have seen these things in Young-Mills theory when you describe solitons or instantons. So small diff anomalies are proportional to, well, let me mention something first. So we have Weyl invariance in this theory, right? We have Weyl invariance. Suppose we are actually able to do the gauge fixing. We end up with a locally flat worldsheet and some 2D theory on this worldsheet, a two-dimensional QFT in a locally flat manifold. Because Weyl invariance is a kind of local rescaling, after gauge fixing, you end up with a residual symmetry. Now it's an actual symmetry, which is conformal symmetry. Conformal symmetry. Which means that the worldsheet is a conformal field theory in 2 dimensions, right? Now, why is this important? Because I'm gonna, conformal field theory teaches us 2 things. One is that there is a number that characterize, actually 2 numbers, the left moving and the right moving number, that characterize roughly how many degrees of freedom the theory has. And for a free theory, just roughly how many fields you have, degrees of freedom. But for a strongly coupled theory, it can be different. These numbers are called the central charges, right? It's roughly a general counting of degrees of freedom. I cannot go into more details, unfortunately, but these numbers are crucial. They are well defined for our conformal field theory. Another thing is that now the operators in the theory, states in the theory, can be classified by the symmetries of the conformal group, which contain the scaling weights, right? So they contain the left moving scaling weights and the right moving scaling weights. And then there's a third thing. Let me try to remind myself. What was the third thing? Yes, this is a super important thing that I will tell you about later. So why did I tell you this? Because the diffeomorphism anomalies are proportional to CL minus CR, which means that the central charges must be equal by anomaly cancellation. This is because, you see, the worldsheet is not just a CFT. It's a CFT coupled to supergravity. And therefore, this becomes a gauge redundancy that must be anomaly-free. This is super important. Large diffeos are classified by the diffeomorphisms that are not small. And this is a group called the mapping class group of the worldsheet. And we will need to gauge this away separately. Like we need the theory to be invariant under this thing. And we will care about this later. Okay. And finally, there are Weyl anomalies. So the Weyl anomaly cancellation is proportional to CL plus CR now. And it must be 0, which means that both are 0. Right? Again, this is completely forced on us by anomaly cancellation. There's no choice. Now, finally, I can answer what a string vacuum is. So what is the story with this central charges? Well, you see, we have a bunch of fields in our theory, some of which are weakly coupled, the ones in space-time. So what does, let me call this C without referring to left or right. The general C is going to be the C of the space-time fields, which is proportional to how many there are because they're weakly coupled, plus the ghosts. So once you gauge fix, you have ghosts for the bosons and the fermions called super ghosts. And the total must vanish. Now it's cool results time. So what is this? I said it's proportional to how many fields you have. But by local Lorentz symmetry, how many you have is proportional to D, the dimension. So you see you have the left moving and the right moving. And if depending on whether you have only bosons or you have the superstring sector, it's either D bosons, or D plus 1/2 D, because fermions contribute half as a boson to the central charge. So it's either, so for both sectors, it's either D or 3/2 D, depending on which sector you have, plus curvature corrections. Because this is a weakly coupled theory, but there are going to be corrections to the central charge in a perturbative expansion. And the ghosts and super ghosts have. So let me write it differently. For both left and right, for a bosonic sector or an RNS sector, you have D or 3/2 D plus alpha prime corrections in all the curvatures, right? That's the weakly coupled spacetime part. The ghosts, well, for a bosonic sector, you only have the bosonic ghosts, which turn out to contribute -26, just a fact of life. For the RNS sector, they contribute -15, because it's now ghosts and super ghosts together. They do -26 plus 11. They go -15. The total must vanish. Oh, sorry, I forgot something. The internal sector, remember, other stuff. See, that was important. So see other stuff. Now this is gotta vanish. And by unitarity, this cannot be negative. This is a fact about central charges. You cannot have negative central charges for a unitary theory. See, everything is important here. Every little detail is important. So what do we conclude? Well, in a perturbative expansion, things must satisfy equations order by order. So the leading order must work. What's the leading order? Well, let's say 3/2 in brackets, so either 1 or 3/2, depending, times D must, you see, plus, well, minus, let me put it like 26 or 15, depending on, let me write it like this, 1 or 3/2, right? Bosonic and superstring, 26, 15, plus something non-negative must be 0. So this must be non-positive, right? Because if you sum something non-negative, it must vanish. Yes.
That unitarity proves that C stuff is greater than or equal than.
Exactly. So
and I see that the ghosts don't have to be unitary. But what about the other C?
This must be non-negative. Yes. Actually, this must be strictly positive, because otherwise D would be 0. So this is strictly positive. Ghosts can be non-unitary because they will decouple from the observables, as in. So this cannot be non-unitary, which means that we have this bound. And if you solve this, you get a bound like D is less than some value. Well, actually, the value is 10. For if you include, if at least one sector is RNS, the bound is 10. So there you go. If you have some tame space-time, D has this bound. And you see, if D is exactly 10, this central charge is exactly 0, which means that there is no other stuff. So 10 dimensions is the maximal dimension for a tame weakly coupled, closed string, etc., with classically stable vacuum. And it's the simplest. It's not the only option, but it is the simplest option, because there is no other degree of freedom that you can add. If you go lower, you must have some other degrees of freedom. They could be extra dimensions. You just change this or not. That is this is the result. So now, now we can finally close by stating what a string vacuum is, I think. And then tomorrow, I will talk about the states of the theory and how gravity is universally present, and how the low energy description of this gravity contains general relativity, plus matter, plus gauge fields, and whatnot. Sounds good? So what is a string vacuum? Like, let's recap what we just did. I have a couple minutes. We constructed this framework because it was, the natural counterpart of field theory without a space-time action, because in this case we cannot use it. So we have weakly coupled strings in space-time described in this way. There must be a space-time sector, it must be weakly coupled. Great. Anomalies must cancel, and we end up with this condition. Now, the space-time sector is pretty much done now. That's it. Up to this, bosonic, like whether we have a superstring, like RNS superstrings or heterotic superstring. That's basically the only option. We throw out bosonic strings. We have this bound. Now we can restate things in a more convenient language. We can say, we know what this is. This depends on D. That's it. Or the discrete choice of heterotic or RNS. This is also fixed, right? It's just the ghosts. So this is the only thing we can have, right? So let's now, focus on that part, the part that we ignored completely so far. So if you will, now after we established these consistency conditions, the worldsheet theory, the CFT, the conformal field theory in the worldsheet, after the gauge fixing, which we can now do because the theory is anomaly free, the CFT is essentially given by this. The rest is completely spelled out by one number, pretty much, or two numbers. The dimension and what kind of string it is, RNS or heterotic. That's it. So the part that we care about, that other stuff, we call the internal CFT, in analogy to the internal degrees of freedom of the string. So well, can I take like 1 minute? Okay. So the internal CFT is what determines my entire worldsheet, basically, if I fix D and what kind of string it is. So these are the string vacua, the possible internal CFTs. There you go. So what kind of central charges must they have by this anomaly cancellation? This is called criticality, by the way, critical central charge. Well, if you do the math, they must be whatever compensates for this. So the internal CFT must have central charges, CL, CR, equal to what? Well, for RNS, it's just 15 minus 3 half D and 15 minus 3 half D. They must be the same because the two sectors are of the same type. For heterotic theories, they must be different. Because I wrote it somewhere else, but the point was like the supersymmetry that I was gauging was 1, 0. So the left moving and right moving waves are, one is supersymmetric and the other is bosonic. So this one is 15 minus 3 halves D, and the other is 26 minus D. Right? This is the ghosts and super ghosts, and this is the bosons and boson fermion pair. So this is the condition for anomaly cancellation of Weyl transformations. What about diffeos? Well, once we have criticality, local diffeos are fine. What about this? When can I cancel this? I can cancel this when my path integrals over sigma are invariant under this. Turns out, it seems like it's a complicated thing because I have to classify all topologies of sigma, and for all of them, I gotta have invariance. Turns out, for closed-oriented strings, is enough to require one condition. This is actually an if and only if with the, my partition functions or path integral are invariant on sigma topologically, homomorphic to just a torus. So all I need is that this particular topology be safe from large diff anomalies. This implies that all of the other topologies are safe. And you see, topologies for a closed surface means the number of holes. That's it, number of holes. Number of holes, in analogy with the Feynman graphs, is the number of loops. So this is a one loop statement. one loop statement. So loops in string perturbation theory, we'll see this tomorrow, are classified by the holes in the worksheet, at least in closed strings, which means that one loop safety under this condition is enough to all loops. This condition, so the mapping class group of the torus, so the group that defines the large diffeos is called the modular group, which means that safety under these anomalies is called modular invariance. So the internal CFT, because this the spacetime part is fine, we will compute this tomorrow. The internal part must be also fine, must be modular invariant. So the internal CFT, which describes my string vacuum, must be critical in the dimensions and modular invariant. And furthermore, you see, it must be at least one sector needs to be supersymmetric. So we can call this a supersymmetric conformal field theory or superconformal field theory. And now this is the definition of what a classical string vacuum is. It's a superconformal field theory with a discrete spectrum, with critical central charges, and a modular invariant torus partition function. This is what a string vacuum is. Yes.
Get rid of the
So, good question. The reason is that this is the internal CFT part. Then the spacetime part and the ghosts contribute in such a way that you get 0, 0. Yeah, I'm done, by the way, if you have any questions. Yeah. Right. Very good question. Thank you. So it was a bit quick because of lack of time, but you see, in the world line, different theories give me different space-time QFTs because I can put different degrees of freedom. On the string, you see, I don't have this freedom to add the vertices how I want, and I don't have the freedom to add the, whatever fields I want. The interactions are completely fixed by the worksheet topology. There is no freedom. I'm not adding it. The interactions are completely determined, whatever they turn out to be. Which means that the only information I can choose is the worksheet CFT itself, the internal part. The external part is a space-time description. And you see, if you look at the action for the space-time part, you get like a metric, a B field, a dilaton. These are fields in space-time. So for instance, if you change those, what you get is a different background fields in space-time on top of which the string propagates. By analogy, the internal sector is the same. It's like extra things on top of which the string propagates. So it's a different background on top of which you do perturbation theory. By definition, this is just a background or a vacuum. This is why. So this internal CFT can include other kinds of fields like that for extra compact dimensions, for example. So this is why. I hope it's clear, but we can chat about it. So yeah, so a classically stable string vacuum in a weakly coupled string theory is this. It's compact, it's a discrete spectrum for other reasons. Compact superconformal unitary 2D theory with these central charges and modular invariance. Now, this is kind of an abstract definition, right? It's a bit wild. But it includes the cases that we know. Like, for example, you can put this to be just flat spacetime, and like a non-linear sigma model, for example, on some manifold will have these properties, can have these properties. And then you see these are basically, it's the string theory analog of the equations of motion for the theory. Like in the, you see that this condition has curvature corrections, right? The curvature corrections tell you that the space-time must satisfy the Einstein field equations plus corrections. And this is nothing inherently stringy. Also, the world line has this property. The string has the difference that it doesn't just give you the classical field equations, it gives you the string corrections to them. Still classical, but higher derivative. It gives you an effective field theory. So the field equations will come from this piece. This fixes other constraints. So we'll see that tomorrow when we derive the spectrum and the low energy and high energy dynamics of the theory. This was the construction of the theory. Okay, cool. Thanks.
In principle, you can add the interaction with higher speed field, the Lagrange that you wrote. For instance, if the thing is coupled to the tachyon, you can write the interaction with the tachyon.
Absolutely. In the bosonic string, you can do that.
Yeah, but
You would, like you could think of writing that, except the state operator correspondence forbids you from that because the tachyon is not in the spectrum of physical states. So if you want to preserve the state operator correspondence, you can't do that.
you can add the speed 4, coupling of the string of the speed 4. And in fact, you add all the possible coupling of the string at all the states.
Sure. But this is the most general action compatible with an effective field theory description, where with the soft theorem of Weinberg tells us that the only space-time fields we can have are up to the graviton. The rest must decouple.
But the string is coupled also to the masses.
I agree, but that's not part of the effective field theory sector. You're completely right. I'm just saying that sector is the same nice weakly curved low energy space-time part. Everything else is in the other stuff.
Mean that you want to integrate out all the massive division fields.
Yes, at low energies at least. Then tomorrow we can do the high energy scattering and they will matter very much. But you can think of them as included in the other stuff part of the. Like I want to separate the stuff that survives at low energies from the new physics, so to speak. This is the.
If you compare with the board line, in the string case, you can couple the string only to states which are the state of the string.
Exactly.
You cannot couple with states which are not of the state.
Absolutely, yes. This is
This is important.
exactly, which is what I'm going to talk about tomorrow when we discuss the spectrum. Yes, the state operator correspondence. Yeah. This is one of the reasons why the 2D quantum gravity implies the space-time quantum gravity, because here states do not correspond to operators. Here they do. So there's a correspondence between states in 2D and states in DD in space-time. This is crucial. It leads to the existence of the graviton and so on.
It's 26.
This is not 26.
That comes from the square of the BRS charge.
You can also get it from, well, it fixed the upper bound, I would say.
Yeah, but it seems to be inconsistent, minus or equal.
But it's not inconsistent if you have extra degrees of freedom in the CFT. That's what I'm saying. Like you have other terms in the CFT. Again, if you only have almost flat space-time and nothing else, D is 10. That's completely true. If you have in an internal sector, an internal CFT, D must be less than 10 by unitarity.
Then it means you compatify or
You may, or you may substitute an internal manifold with an abstract CFT. It need not be a sigma model on some manifold. It can be, for example, a Gepner model or a Norbifold point of some weird or Landau-Ginzburg model. You can have many things.
doesn't mean that the total PRS charge must be 26.
Well, yeah, of course. The central charge of the super Virasor algebra must be 0, yes. Absolutely. And in the BRST formalism, you can see is from nilpotency of the BRST charges. Absolutely, completely.